The growth rate of the bacterium that I cannot pronounce, a common bacterium found in the human intestine, is proportional to its size. Under ideal lab conditions, when this bacterium is grown in a nutrient broth medium, the number of cells in a culture doubles approximately every 20 minutes. For question A, if the initial cell population is 100, determine the function Qt that expresses the exponential growth of the number of cells of this bacterium as a function of t in minutes. In order to determine the function Qt that expresses the exponential growth of the number of bacteriums, we'll need to express a function like this with a Qt equals the initial population, which is Q to 0 at time equals 0 times, since we're doing an exponential growth function, we'll do e to the kt, which is t in minutes and a constant. And then we get that, and we can substitute in 100 for q of 0, because 100 is the initial velocity as expressed in A. And then here we have our function qt. From the text up here, we know that the cells in a culture doubles approximately every 20 minutes. So for that, we'll substitute in 20 for t, and that'll leave us with, because it doubles every 20 minutes, do 2 times the q initial that we have up here, which will equal 2 times 100, which equals 200. So basically from that, we can do Q20 equals 100 times E20K. This is from the equation up here. And then for that, we're going to solve for K. E20K equals 200. I'll take that from up here. E20K equals, when we divide those out, equals 2. From here, we'll apply the natural log, which would be ln E20K equals natural log of 2, and that comes out to be 20 times K equals natural log of 2. And K equals natural log of 2 over 20. So that's what K equals. And from there, we'll make our whole function. It'll be Qt equals the initial cell population times E. And this, as it turns out, calculator 0.0346. So we can either put that there or do ln2 ln2 times t. And that's your equation for A. To find out how long it'll take for a colony of 100 cells to increase to a population of 1 million, we'll have to take the equation from part A and set that equal to 1 million. So basically, the equation from A went Qt equals 100 times E, and it was ln2 over 20 up here, but we're going to use a number for it. So 0.0346t equals 1 million. And we'll take that, we'll divide by 100 over here, 100 over there. It'll be E 0.0346t equals 10,000. From there, we'll take the natural log of this. And the natural log of 10,000. And then basically that will leave us with the number from up here, 0.0346 times t equals natural log of 10,000. Then from there we'll solve for t. T equals the natural log of 10,000 all over 0.0346. And that's your answer right there for B. For question C, if the initial cell population were to change to 1,000, this would not alter our model much. Basically, we'll take the equation from the first problem, which was QT equals the Q initial times e to the KT, which is time in a constant, equals 1,000 as the initial here, instead of 100, times e KT. So basically, every 20 minutes, the initial cell population doubles. So basically, we do Q20, just like we did with the first problem, times 2 times Q initial, which equals 1,000 was the Q initial, that'll equal 2,000. And then if we set our equation up here, equal to 2,000 down here, be 1,000 times EKT equals 2,000. We take T out actually here because T is 20 up here, I forgot. But right down here, we can start again. It would be E20K because we'll divide by 1,000 up here. That equals 2. Take the natural log of each side. And you're left with 20 times K equals natural log of 2 there. We can solve for K equals natural log of 2 over 20, which is the same as we had in our first problem. So because the constant does not depend on the initial population, we can conclude that the constant K depends on the rate of growth instead of the initial velocity.